My name is Borbalace, and today we have Artemis Spyrou in this seminar. And she is a professor of physics at Michigan State University at the Facility for Rare Isotope Beams, FRIB. She obtained her PhD in 2007 from the National Technical University of Athens in Greece and has been at MSU ever since. Her research focuses on nuclear physics experiments that are important for understanding astrophysical processes. Since 2015, she also oversees the outreach activities of FRIB and is active in public engagement opportunities. In 2021, she was selected as a fellow of the American Physical Society. And today she will talk about neutron-capture reactions constraints for astrophysical processes. So Artemis, please, the stage is yours.
Thank you, Borbala, and yeah, thanks for inviting me. I'm always happy to share my favorite topics here. Let me share my screen. You can see, okay?
Yes, perfect.
Let me put things out of the way here. Okay, so let me get started. I'll talk about neutron capture reactions for different astrophysical processes. So I'll kind of introduce the topics as we go. But first, I wanted to start with, I decided to try my luck with ChatGPT and see what we can what I would get out. And I was trying to make this analogy for how the field of nuclear astrophysics works. And the analogy is that it's as if we have a soup. We can call it our cosmic soup. And the soup has different ingredients in it. And what we are trying to figure out is what those ingredients are. And so in our case, it would be the various elements we see, but there are contributions from many different elements, but also many different astrophysical environments. And we are trying to understand how that soup was formed. Now, ChatGPT didn't have a good concept of what the periodic table of the elements was. So you can see over there what it came up with. It kind of looks like it, but it's, yeah, that was quite a little challenging for it. But overall, I think I got the picture that I had in my mind. Now, on top of just the big picture and the big idea of trying to get the figure out the cosmic soup, we are in the era that is called the multi-messenger astronomy era. So in the soup analogies, it's like trying to analyze our soup in many different ways. So we can smell it and we can taste it, and we can even get some of the ingredients and look at them through the microscope or do x-rays on them. So you can get as much information as you can to, again, try to answer the question you're trying to answer. So in our field, in the multi-messenger astronomy era, this would look like trying to get as many signals and signatures as possible from the universe using as many techniques as possible. And if actually these techniques and these signals are coming from the same source, then even better, we can really constrain that one problem or that one stellar environment from many different points of view and combine the information. So that's kind of the idea. So the information we're getting and the signals, so the messengers that we are getting, of course, is solar system abundances. This is kind of the most basic thing, not just elemental abundances, but actually isotopic abundances, and we can learn a lot from that. We get stellar observations, and I'll come back to the particular stellar observations later, but we get stellar observations from a variety of stars, and depending on the properties of these stars that we're looking at, you can again learn different things. We've had gravitational waves for the last not quite decade, and together with the gravitational waves, we also get light curves. And so this is again not just light curves, but now we get them, as a function of time, and we can point to particular events and do combinations. Like the one obvious one is these gravitational waves with the light curves that we got from the GW 170817. We get cosmic rays. That's another signature. We get gamma ray observations. And we even get signatures from within the solar system, not just abundances, but additional, we get radioactive isotopes from within the solar system. And there's more. So these are just a few examples that we are trying to combine the information from the different observables to figure out how our cosmic soup was cooked. What was the recipe and what were the ingredients? So starting with the chart of nuclei here, as we usually do in nuclear astrophysics, I will not talk about the stellar burning of the production or the synthesis of the lighter elements. I will focus more on the heavier elements. So in heavy element nucleosynthesis, from the beginning, from the 50s, there were 3 processes proposed. It was the S process that goes right here, the green line along the valley of stability. It's the R process that goes quite far from stability. And then the P process, this kind of weird process that starts from the top coming down. So it's a process that through photo disintegration reactions, it gets all of the isotopes that were formed by the S and the R process and kind of breaks them to produce more proton-rich isotopes. And at the time, and actually until maybe a decade ago, we thought that this is more or less complete, and this picture could explain most of the observations we had. Not everything, but most. And so this has been kind of, the community was happy, and we were still trying to figure out details and what is the side of the R process, what is the side of the P process, how far do they extend up in mass, et cetera, et cetera. But it was a kind of a complete picture, more or less a complete picture. Now, all the observations that I had on the previous slide, as time goes by, we get better and better at all of those observations. We get better and better at all things. But in terms of observations, as we get better, we started to see signatures where these 3 processes were not enough to explain those observations. And this is where we realize that things are a lot more complex than what we thought previously. And so if I add a few more processes that now we know and we have signatures that show that these processes also contribute, you can see that like on the proton-rich side, we have the RP process and the NuP process, different environments, different processes, but kind of go along the same path here. The weak R process here for the kind of intermediate masses, the I process that I will come back to later in the talk. And there are more. I didn't put all of them. There are more. But the idea is that there are a lot of the nucleosynthesis picture is a lot more complex than we thought. And our goal is to disentangle all of these contributions and figure out what contributes where, again, how far these processes contribute, what part of the chart of nuclei or elements are producing, and if and where they could be contributing to our own solar system. So this is the big picture. Diving more into the nuclear physics aspect of things, since I am an experimental nuclear physicist, we need to understand the properties that are needed in order to understand all of these different processes. So on the proton-rich side, typically we need the masses of the nuclei involved, we need beta decay properties, and then we need reactions that involve proton or alpha particles. On the neutron-rich side, it's the same, masses and beta decay properties, and we need neutron-induced reactions instead of the protons and alphas. Fission properties, sometimes there's alpine reactions involved. So again, we have a list of different reactions, and depending on the process, you might need different things. One thing I didn't mention earlier is the color code on this chart of nuclei is that the kind of greenish, bluish color here in the background shows the region where we have some kind of experimental information for these isotopes. And it's interesting to see that many of the processes, a little bit the I process up here, definitely the R process, the weak R process, they extend in regions where we don't have any experimental information right now. And this is actually where nuclear theory comes into play. If we can't have the nuclear properties experimentally, then we have to rely on nuclear theory. So again, back as an experimentalist, the name of the game or our role is twofold. One is to work with astrophysics modelers, identify the specific properties that are important, and maybe try to measure those specific properties that are important. And second, if we can't measure those properties, then we work with nuclear theories to try and constrain those nuclear theory models so we can do a better job predicting those properties. So this is kind of how the life of an experimentalist, how it works. In this talk, I'll focus on neutron-induced reactions and specifically neutron-capture reactions. And I will focus on 3 topics. The R process, I'll give you a little status update. I'll tell you already we don't have results yet, but I'll tell you kind of how we're getting there. I process, I'll show one example of a result that we had last year. And then I'll talk about the nucleosynthesis of massive stars through the iron 60s. So let's dive in. R process. I think that's our standard thing. The R process is responsible for the synthesis of about half of the isotope of heavy elements. So it's important. It makes half of those isotopes. And until recently, we didn't really know its site. There were predictions and guesses, but not a solid proof. Since now 8 years, we have at least one verified site of the R process, but there's still questions. What is the site of the R process in general? Is it just one, or are there contributions? Probably there are contributions from multiple sites. Is it happening in one set of conditions or multiple conditions? Probably it's multiple sets of conditions. And then how do all of these mix together and contribute, and what kind of abundance patterns do we get, and what does that look like for our own solar system? I mentioned earlier, I showed this picture earlier, but I didn't say much. This is one of the most impressive pictures we've had in the last few years. This is abundances, or one star, abundances coming from one star. You can see the name of the star over here, the HD 222925. And it is the most complete set of abundances we have, even more complete than the solar system, which is quite a statement to make, but it's true. So let me tell you a little bit more about what's going on here. This is a carbon-enhanced metal poor star, so CEMP. And the point of CEMP stars is that these are very old stars, and the hope is that they are only enriched by a single process, as opposed to, for example, when we look at the solar system, where the solar system has contributions for multiple processes, even multiple generations of stars contributing. So when this is really, our solar system is really a soup, and we can't figure out, or no, we can't, but we have all these contributions, and it's more complex to figure out the contributions from each. But if you look at the CMP stars, you can just see, let's say in the soup analogy, maybe one ingredient at a time, and then you can really try to narrow down or constrain your models for each of the processes separately. The problem with the solar system is because it has all these contributions, the solar system abundances for the R process, you get the full abundances, you subtract the S process, and whatever is left, you call it R process. So first of all, you have that subtraction process, which induces a lot of uncertainty. So some of the elements, maybe you have some signature, but they're very large uncertainties. And the second thing is, now that we know that there's so many processes contributing, I'm not sure we can just call it our process and be done with it. Maybe it is, but we just don't know. So maybe there are contributions from other processes as well. So you can see how, looking at the solar system, things are a little more complex, but looking at this star here, it's this beautiful picture of a complete set of abundances, and this is a beautiful R process signature. So I mentioned already the GW 170817 gravitational waves and electromagnetic signals. This is already close to a decade since this observation. I just want to get to kind of the new things that are happening here. So at the time, it was really exciting because it was the first time that we could see a signature of the R process, not just from abundances, from an event that happened many millions or billions of years ago, and we just see what's left in the R process abundances, but we could see live what is coming out of these beta decays that are coming from R process, the R process event. So these beta decays, created a light curve. At the time, it was this blue component and the red component, and putting them together. Now this picture is not as simple as that, and it's more complex, but still, it was the first time we got a very rich set of data that we didn't have before, so that was exciting. Now, on top of that, astronomers started to look at this the spectra more closely, and they started to see that maybe we can have signatures of specific elements. At the time of the event, the idea was that, oh, everything is just Doppler shifted and everything is so complicated that we can't see individual elements. But it looks like astronomers are finding creative ways of kind of getting out the information from individual elements. This is the first paper that looked at strontium, and since then there are actually additional papers. So this is still, of course, a very active field, and we're learning still a lot more. And the last example of kind of new developments that I wanted to mention is this paper from 2021, which used these two long-lived radioisotopes, iodine-129 and curium-247, combined them. And what they noticed is that if you get the ratio of those two isotopes from meteorites, you are sensitive to the conditions of the art process. And there are different conditions here that I'm not going to go into detail, but basically for the different conditions, you get different values of this ratio. And the authors already pointed out at that time that uncertain nuclear physics data limit our confidence in this conclusion, which again brings me back to the nuclear physics input. So all of these things that I've been talking about, the site, the conditions, the light curves, all of these have nuclear physics inputs, different kinds of nuclear physics inputs, and it's our job to try and constrain so that we can do a better job modeling and understanding the art process. So what kind of nuclear physics inputs? There are many different things that we need from nuclear physics, and most of them are not known. I showed this picture before. Again, the color code is, if we know anything about the isotopes, there's a color to it. If we don't know anything about them, it's the gray line, the gray color. And you see the art process line. It's just a cartoon line, but still you see how it goes into regions where we do not have access experimentally. We need a lot of information for all of these isotopes. And so this is where the community is going in the future, trying to get access to all of these isotopes and measure these quantities. And this is what we are excited about as experimentalists with the new generation facilities. One, for example, is FRIP here at MSU, the Facility for Rare Isotope Beams, which this line here, the gray line, is how the expectation for how far FRIP will give access to these isotopes. So it's really exciting. It basically touches on almost all the isotopes involved in the art process. So it's really we expect that in the next few years, we will be able to do experiments out there and really provide stronger constraints for the art process. Another facility that is coming up in the next year or two is this N=126 factory at Argonne National Lab. Again, this is a general region where we expect to have new isotopes. And these are the two facilities here in the US. There are other facilities around the world that are trying to do the same thing. Okay, so one problem that we have is has to do with these neutron capture reactions. If, let's say, my facility, FRIP, produces an isotope right there, I can go and measure its mass, and I can measure its beta decay, and maybe I can do fission property measurements depending on the beam rates. But if I have enough beam rate, I can do all of that. There's nothing I can do to get a neutron capture rate for that isotope at this moment. Maybe in the future, but at this moment, there's nothing I can do. And the reason is simple. It's an experimental reason. In order to do an experiment to measure a neutron capture reaction, what I need is to have, let's say, a target, a heavy nucleus target. I shoot a neutron beam at it, and I measure what comes out, and I can measure the neutron capture. But if my target, which is somewhere out here, lives for 100 milliseconds, it's not enough time to make a target and actually do an experiment. I can make that 100 millisecond isotope, I can turn it to a beam, but then I would need a neutron target, and that also doesn't exist. And the last chance is to do a beam on beam kind of experiment, but so far we don't have enough yield to do those experiments. So we're kind of stuck. It's a pure experimental constraint, but we are kind of stuck. There are new facilities that are being developed around the world trying to address this issue, so we can do these neutron capture measurements on radioactive isotopes, but we are not there yet. So right now, we don't have access to these neutron captures directly. So, and as a result of that, when you look at the chart of nuclei and you look at which neutron capture reactions have been measured experimentally, you get a very small fraction. So this, of course, means that the reactions that are involved in any of the astrophysical processes are not very well constrained. We have to rely on theory, and we need to go and constrain that theory. So the same game that I mentioned in the beginning. And this is what we're trying to do. These measurements where we try to put constraints, even though we don't measure the reaction directly, these are called indirect techniques. And I'll go through a few in the next slides. So if I want to measure or understand a neutron capture reaction, I can describe it like this. Here's the target nucleus that we're interested in. The neutron capture will bring us to some high excited state in the final nucleus, maybe sitting over here. And then from this state, the nucleus will de-excite emitting gamma rays. So if I cannot measure this reaction directly, I can look at the ingredients that are needed to describe this theoretically and try to constrain those. So one ingredient we need, for example, is called the optical model potential. And that describes how that neutron will interact with the target nucleus. It turns out that for most of the applications we have, this is relatively well known, or as far as we know, maybe it's not so well known, but so far, the optical model potential models that we have seem to be working, and we'll see in the future how that goes. A second ingredient we need is what is something called the nuclear level density. So how many levels do you have available here and all the way down in your nucleus? So it's this neutron capture. And of course, if you have more levels, then you would have a higher probability to capture into one of these levels. And so this quantity is an important quantity. The second important quantity that we are looking at is this gamma ray strength function, which is basically the probability to emit gamma rays of different energies. So once you populate the nucleus, how will this nucleus de-excite emitting a bunch of gamma rays? Or maybe the nucleus will not de-excite emitting gamma rays, and it will just emit a neutron and go back where it started from. And of course, that's not a neutron capture anymore. So you can see how looking at the details of the nuclear reactions matter. And if we can measure some of the ingredients, specifically we're looking at the first two here, then we can provide a constraint. Let's see what this looks like if we don't have any constraint at all. And I'm showing here the example of cadmium-127 and gamma reaction. Each of these lines uses different combinations of level density and gamma ray strength function models, predictions, to predict the cross-section of this reaction. And you see that the variation of this cross-section is more than 2 orders of magnitude. So again, if we don't have any experimental constraints, this is the best that the theory can do right now. And we don't know, we can't constrain it anymore. So this is the uncertainty, let's say, or the variation when we use theoretical models to predict these neutron captures for the art process. So we are trying to do better than that. We are trying to constrain the level density, constrain the gamma strength, and reduce this giant band here from 2 orders of magnitude to make it as good as we can. So that's the idea. There are many different ways to do that and different techniques, and I'm not going to go through details for every technique, but there's something called the Oslo method and another technique called the Surrogate method, and these use reactions. So some kind of reaction to populate the nucleus of interest, and then measuring all of those gamma rays, try to provide some constraints for the reaction. Another way is called the Coulomb dissociation, where you start with the nucleus of interest and you excite it up, and then either measure gamma rays, but usually measuring the neutrons that are coming out. There's another method called the shape method, which looks for the individual gamma rays as they populate the discrete levels down here. And that gives us it's called the shape method because it gives us the shape or the energy dependence of the gamma ray strength function. And then finally, the method that I'll be discussing is the beta Oslo method. So it's this Oslo method, but populating the nucleus using beta decay instead of using reactions. Let me show a little bit the complementarity of these methods. Actually, starting here, the color code on my next picture is basically the ratio between the top prediction here and the bottom prediction here. So for the cadmium-127, this would be roughly a factor of 100. So this is the color code here. So the factor of 100 is these red boxes, or more than 100. And then you see the different colors going all the way down to less than a factor of 5 in the variation between the models. And of course, those are the nuclei that are right along the valley of stability, where we have very good constraints from experiment. And so the theory is well constrained. The problem comes when we try to get all of these models and extrapolate left and right here to unstable isotopes. And when we do that, then each model will extrapolate in a different way, and we get large variations. So coming back to the techniques, stable beam reaction-based techniques like the Oslo method or the surrogate method, they would constrain reactions here. So you do get a few steps away from stability, and you get very valuable information for the isotopes either in between stable or a few steps away from stability. Then we could have radioactive beam-based experiments, again, using reactions. And with those, you can get maybe a few steps more away from stability, but soon you run out of beam intensity and you just cannot go that far. And then finally, with beta decay, then we can really reach to the more exotic isotopes, because with beta decay, we can do these experiments with very low beam intensities. But even that has its limits, because as you go to the right here, the nuclei, the neutron separation energy for nuclei becomes smaller and smaller, and then you just don't have enough gamma rays to apply any of these techniques. So you can kind of see the range and how all these different techniques are complementary. Let me dive a little bit into the Oslo method. And I'm not going to go again into details because it will probably take another full hour to explain all the details of the method, but just to give you an idea. The Oslo method starts with this matrix. This is kind of our starting point. It has excitation energy of the nucleus on this axis, so just excitation energy, and then the individual gamma rays on this axis. So we know from every single excitation energy what kind of gamma rays are emitted. So the method, there are different steps to the method, this unfolding and iterative subtraction. I'm not going to go into that, but the main idea is that we end up with a distribution of gamma rays that all come from the same beam, and it's only the first gamma ray. We don't really know which the first gamma ray is in our experiment, but we can get the distribution of those gamma rays. So the probability to emit this gamma ray, for example, in the nucleus, will depend on the level density down here and on the gamma ray strength function for that particular energy. So these are the two quantities that we're interested in, and this is what comes out of the Oslo method. And so once we do get those two quantities, we can extract a neutron capture cross-section. And this is a case where we compare to existing experimental data, and you can see it works very well. So that's kind of just the basic idea. When we do this with beta decay, there are different complications and whatnot that, again, I don't want to bore you with the details so we can get to some results. But we need something that is called a total absorption spectroscopy, which is basically collecting all of the energy available in gamma rays. And this way we can get our excitation energy, which is this axis here. So again, same thing, just modifying it for beta decay. I'm showing here as an example, let's say the reaction we're interested in is nickel-69 and gamma. The half-life of nickel-69 is 11 seconds, so we can't really do much about it. But we populated the compound nucleus through cobalt-70 beta decay, and then we get level density and gamma strength for this nucleus. The way we do this is through a gamma ray calorimeter that looks kind of like this, and I'll show real pictures later. And so the idea is that you implant your cobalt-70 here in the center. Then when it beta decays, it emits a whole bunch of gamma rays that belong to nickel-70. And we collect all of those gamma rays. We collect the individual gamma rays because we have different isolated segments. And we collect the full energy that's deposited in the detector. And this way we get that matrix that I showed earlier for the Oslo method. And this is kind of the basic idea. The instrument we use for these measurements is called SUN. It's the summing sodium iodide detector. It looks like this. It's not very large. This is only 40 centimeters or 16 inches, and the same in height. And there's a tiny hole here. It's less than 2-inch hole, and this is where the beam comes in and gets implanted at the center of the detector. It's important. Recently we went through an upgrade of SUN. Now we have SUN++, and basically we got the two halves. We opened them up and we filled them with new detectors. 8 of them are cerium bromide detectors, which give us better time resolution and better energy resolution. Together with SUN, we have Suntan, the tape transport system, and this is used to remove any kind of daughter and granddaughter decays so that they don't contaminate our spectra. We have Sunspot, which is an electron detector that goes at the center of SUN. And since we don't have much space here at the center of SUN, we get optical fibers to collect the signal and get it into PMTs that are sitting outside of SUN. This is what the beam sees, by the way. This is the tape, and this is sunspot around it. And we have a silicon strip detector. We don't have a fancy name for the silicon detector. We just call it mini DSSD. And that's for, again, a different type of experiment, but again, to measure the beta particles implanted at the center of SUN. Okay, so I wanted to share a couple of new developments that we had, which are exciting. We've been using SUN and the Beta Oslo for now it's 11 years. So we have a lot of results. I wanted to share a couple of the new results. The first one is this is not with SUN, but it's the first use of the Oslo method with charge exchange reactions. This is Remco Zager's group here at EFRIP. So instead of populating the nucleus with any kind of other reaction, Remco and his group use these charge exchange reactions where a proton is converted into a neutron or vice versa. And it's the first time we even tried to apply the Oslo method with these reactions. This is the work of Nishad here in Remco's group. And Nishad used this T-helium-3 reaction to populate zirconium-93. It's these green data points. Let me just show Nishad results first. So this is the zirconium. So measuring the zirconium-93, Nishad could constrain the zirconium-92 and gamma reaction with this charge exchange Oslo. And his results, which is this blue band here, are a very nice agreement with existing measurements. There's this green set of data that I don't know why they're different, but overall, we're in good agreement with the other measurements. Now, we also did beta decay feeding zirconium-97, and these are the yellow points, and this is from my group. Amal Sebastian was the student working on this, and you see a very nice agreement with previous data. And this is the first time that we have a very nice way to compare a reaction where the neutron capture has been measured before, and we have access to the nucleus through beta decay. And so this is still preliminary, and we don't have the full band of the uncertainty band, but as a first result here, you can see that we are matching nicely the previous measurement. So this is another nice validation of the Beta Oslo method. So I mentioned the technique has been around for a little over a decade. We started with a focus on the weak R process region. This is work by Rebecca Serman and collaborators, identifying a region within the weak R process where neutron capture reactions are important. And we started with this region just simply because these were the beams that were available at the time, intense beams that were available, and we had several results in this region. And now I'm very happy to say that we are able, with EFRIP, we already were able to extend these kind of measurements to higher masses. And the first experiment we completed that last June, and we attacked the region right around tin 132. So these were the isotopes that are included in the proposal, and we actually managed to do even more than what we had originally in the proposal. So this was the proposal, and as it happens, those same isotopes are also important for that meteorite study that I showed you earlier. It's those same isotopes happen to be important for the production of iodine-129. So this was kind of the full constraint of multiple observables within the R process. So we use Sun++ for that. The experiment was just completed last June, and I just want to show you some preliminary pictures from online results. I obviously don't have results yet, but this is what the setup looked like. We used the mini DSSD at the center of Sun. This is what Sun++ looks like inside the shielding. This is a shielding from a different detector called MTAS. You see 3 students are responsible right now for the data analysis. So we're going through calibrations. It's a complex setup, so we're going slowly through calibrations. And Jessica Costas and Chris are working hard trying to finish the calibrations, and then we will attack the isotopes. This is just 1 hour of data. We ran for 4 days, so we got a lot of data. And actually, together with this setting, we got a second setting a little bit shifted to the left here. So we expect to have about 15 isotopes from this data set. So this is really exciting. But this is all I have for now. Maybe in a year or 2, I can give more results. Okay, so that's all I had for the R process. Let me just spend 5 minutes each on the I process and the RN60 and then wrap this up. So I mentioned the I process is one of those new processes that were introduced because we have observations that are not, we're not able to explain just with S and R process. So this is one example from Ian Rotter again, where the data points are observables and they could not be reproduced by just S, R, or a combination of the two. Another example, this is actually earlier, it's from 2000, which looks at presolar grains. And again, they have a weird pattern that they have some isotopes enhanced, which they don't see an enhancement in all S or R isotopes, they just see a different pattern. And then finally, this is an example of this lanthanum over europium and barium over lanthanum, this double ratio plot that astronomers use. And every data point here is a different star. And this double ratio, this plot is just sensitive to the neutron density, to the conditions. So if you look at low neutron density for S process, you end up in this region. And if you look at R process, you end up in this region. And there's a whole set of stars that do not match with S or R or a combination of the two. And so these are the stars that are the candidates for this intermediate process or I process. Actually, our colleagues at the University of Victoria, Paul Herwig and Pavel Denisenkov, they did a whole study where they varied the neutron density, and they start from this blue color here. You see that the neutron density is the color code. And so they start from S process neutron densities, and they go all the way to R process neutron densities, which are these reddish colors, C10 to the 20. And in between, you see how this line curves around, and it basically matches almost all of the observations, and then you end up in the R process. And this is what kind of the I process is doing. It's these intermediate neutron densities that seem to match to fit exactly where we have observations. So that's where the I process is, it's in between S and R. And we can kind of see the flow over here. Again, it's 3, 4, 5 steps away from stability. And the good thing about this region is that all of the nuclear physics is known, the masses, the half-lives, some isomers, not all of them, beta delay, neutron emission. So those properties are known. The only thing missing is neutron captures. So by measuring 1 or 2 neutron captures, we can learn something, we can have an impact. And this is what we've been working on. So going back to that picture from before, if I just choose a single neutron density, let's say 10 to the 13 neutrons per cubic centimeter, and now we vary the neutron captures that go in it, we actually get a very large uncertainty. You get a whole region, and depending on what the neutron captures look like, you could end up with a result that is all the way out here where there are no stars, or maybe all the way up here, or maybe you end up in the middle, but we have to constrain these neutron captures to know what's going on. So this is what we decided to do. And there's a sensitivity study by Pavel Denisenkov and his group. And it's interesting. Out of the hundreds of reactions in the I process, there's only a handful that would contribute to this plot, to this uncertainty. And so we decided to attack one of them so that we can reduce this uncertainty. We did this experiment at Argonne National Lab. There's a team, there's a setup. And this is just quickly the result constraint of the neutron capture cross-section, and I just want to focus here on the result. So this is the same plot, that large uncertainty that we see if we don't take into account the experimental constraint. And now with this new measurement, this now becomes like this. So you can see how with a single measurement, a single reaction, and not even a direct reaction, it's an indirect measurement with a relatively large uncertainty, but we can still learn something. We could constrain this. So now we know that these stars here in the middle are probably could be produced by a 10 to the 13 neutron density, and we need to dive in. This is still a simple model. We need to understand better, but this is now constrained by the nuclear physics. The next reaction for this region is this niobium 151 and gamma, which affects europium, and my student Hannah Berg is working on that. We're very close to getting some results. Okay, and for the last 5 minutes, I want to share some results that we had. Again, this was published a year ago for the production of iron-60 and nucleosynthesis in massive stars. So when we look at different stars, even the solar system, but even when we look at different stars, if you see in your observations any element, I'll focus on iron since that's our focus here. So let's say you see iron in your abundances, in your observable abundances. You have no way of knowing if that iron was produced in that star or if it was already there in the stellar cloud that where that star was formed in the first place. There's no way of knowing that. But if we use a radioactive isotope like iron-60 that we're talking about here, with a half-life of 2.5 million years, then if you see iron-60 in that star, then you know that it was produced there and didn't come from before. And so these radioisotopes are a very strong constraint for nucleosynthesis because they have this time constraint that you don't have in any other way. So iron-60 has been observed within the solar system. So again, think that it's a 2.5 million year half-life. So it was produced somewhere and it traveled through and it came to the solar system and we could observe it. And we've observed it many, many times. One observation is through cosmic rays. You see a little bit of signal in iron-60 there. Lunar samples. They could see iron-60 on lunar samples. This is from ocean sediment samples. This was pretty cool because they got samples that were enhanced in a special kind of bacteria. They were magnetotactic bacteria that have an enhancement in their iron concentration, and then they could enhance their signal. I found that was pretty cool. And then ocean sediment, ocean crusts, they can get, an age signature based on how deep you go on this crust. And what they found, some things don't have an age signature, but these two results do. And you see how 2 million years ago, there's an enhancement in the iron-60 result, which is pretty cool. There was nothing in the surface, but 2 million years ago seems there was an event that produced iron-60 that ended up here on Earth, and we can see the signal today. And we don't really know exactly what that event is. Maybe it's a nearby supernova. Maybe there's a discussion about our super bubble and how we kind of maybe go through the wall or some border of the super bubble. There are a lot of explanations, and we're still trying to figure it out, but this is an impressive signature to have. And together with all the things in the solar system, we also measure gamma rays. You need to go to space, so it's space-based telescopes, but you can see gamma rays both from iron-60. It's, to be specific, it's iron-60 decaying into cobalt-60, and then we see the gamma rays, but still. And we also see gamma rays from aluminum-26. Now, we could analyze the signals for those two isotopes separately, but there's benefit to analyzing them as a ratio because a lot of the things cancel out the distance or the number of sources or the absorption while the gamma rays travel through space. So there's a lot of things that could cancel out. And so this ratio is a powerful tool to understand massive star nucleosynthesis. And there's a problem. And the problem is that models consistently overestimate this ratio by significant factors. So one theory or one suggestion is that this discrepancy between models and observations comes from nuclear physics. And the main uncertainty in nuclear physics is this reaction here, iron 59 and gamma producing iron 60. And this is exactly the reaction we decided to attack. So there was a measurement back in 2014 where they measured the gamma ray strength. Remember, we need two ingredients, gamma strength and level density. They measured the gamma strength, but they could only measure it at high energies, so in this region here. And then they extrapolated to low energies with the best knowledge that we had at the time. This is kind of the expectation for the gamma strength. Now, right around the same time, you see there's the paper by Cecilia Larsen from Oslo. It was 2013. It was right around the same time that we started to have signatures where that the gamma strength doesn't actually look like that, at least not for all nuclei. And for some nuclei, it kind of looks like that. And this iron 56. And so we wanted to do an experiment to see which direction the iron 60 will go so that we can better constrain that cross-section. And this is what iron 60 looks like. So it's not quite as strong of an upend as iron 56, but it has a significant upend. And as a result, the cross-section for the iron 59 and gamma reaction is actually enhanced now by approximately a factor of 2, a little less. So when you put this in the models, and we did that together with Carl Fields, who did MESA calculations for stellar evolution, we see the following. I'll just go through the text here. I'll skip the figure. So a factor of 2 higher cross-section for the reaction means roughly a factor of 2 enhancement in the production of iron 60, which makes that ratio of iron 60 over our aluminum 26 higher. And if you remember, the discrepancy between the models and observations was that the models were too high, and now we made it even higher. So we made the problem worse. But at least we've showed that the problem, the discrepancy, is not coming from nuclear physics. The nuclear physics is now better constrained, and we need to dive into the models, the supernova model parameters, to understand a little bit better where the discrepancy might be coming. So yeah, these were my 3 stories: our process, I process, and iron 60. I hope I showed you that nucleosynthesis, heavy element nucleosynthesis, is more complex than we thought before. There's a lot of work still need to be done involving radioactive nuclei, and specifically within the neutron-capture reactions. We're working hard to try and constrain those reactions as well as we can for the different processes. And I'll finish with a list of collaborators, and thank you very much.